All right, well, welcome back to astronomy. For today, we're going to move into talking about stellar evolution. Just to keep you abreast of where we are at the moment, we have talked a little bit about the formation of stars and the HR diagram, and how the HR diagram is used in determining the life cycle of stars, which is what we're going to talk about today. We also talked a little bit last time in the video I posted about our sun, the one star that we can study in detail. And so now that we have all that information at hand, we can move into trying to understand the detailed life cycle of all of the stars that we see in the night sky. Now, in order to do this, we're going to need a little bit of a laboratory, and that's the laboratory we're going to talk about today, or stellar clusters, which is going to lead into your activity for Thursday. Before I go on, I just want to mention that I've moved our exam from this week to the week following spring break. And the reason for that is just that we were running a little bit behind schedule and things were starting to pile up a little bit. So I thought we'd give ourselves a little extra time to make sure that we can understand what's going on. So we'll do the rest of stellar evolution this week, and then you'll get a nice break for spring break and move into just a little bit of special relativity just before we go into the exam review on Tuesday after spring break. And then we'll have the exam the following week. So that's the plan, and then after that we'll move into studying the origin of the universe, dark matter, the possible existence of life elsewhere in the universe, and so on and so forth. So that's sort of where we are at the moment. Okay, so what I'd like to talk about today is a laboratory for trying to understand how stars form, move on to their main sequence life cycle, and eventually expire and return their material to interstellar space. And those laboratories are called stellar clusters. And stellar clusters are places where stars are formed. That's where they're born. We saw that movie a few times ago about the collapse of gas that turns into these stellar clusters. And these stellar clusters are places where you can have a large number of stars form. Eventually, if they're loosely coupled clusters, they'll dissipate and wind up with sun-like stars like ourselves that are just kind of floating around in the galaxy. If there are lots of cluster members, they tend to stay grouped together in things called globular clusters. So we have really two types of clusters that form, these loose associations and these very, very dense associations. And we'll show some pictures of what those look like in the sky. So here's a couple pictures of the Beehive Cluster. It's called M44. And let's see here, let's find a nice one here. So here's what the Beehive Cluster looks like, and it's a cluster of stars that are loosely associated. Now this is something that you can see with your naked eye, so if you go back to Stellarium and get that to work, not when you're trying to present to a bunch of people, you can find that you can find M44 Beehive Cluster in the night sky, and this is something that you can see. You'll see a little fuzzy patch on the sky. You won't see all these stars because you need a telescope, but you'll see this little fuzzy patch because of the dust and gas that seems to be associated with this. So the Beehive Cluster is called an open cluster because it has a loose collection of stars. So they're called open because they're open, they're not dense. They're often sometimes called galactic clusters because they tend to live in the galactic plane. That's just because of that's where most of the dust and gas is forming. Another cluster you may have seen in the night sky is called the Seven Sisters or the Pleiades, and it's also known as the Subaru in Japan. And if you happen to drive a Subaru or see a Subaru, take a look at the markings on the front of the car, and you'll see that it has this kind of shape that looks like that. They've kind of stylized it, but the Subaru is the Pleiades star cluster. And again, if you were to see this in the night sky, it would look a little bit fuzzy, it look a little blue because it has all these bright stars surrounded by dust and gas. Now, one of the cool things you can do, because you are now an astronomy student, is you can immediately look at this cluster and notice that the stars are blue. And because the stars are blue, you know they have to be hot, and because you know something about the HR diagram now, you know that hot stars live for shorter periods of time. So you can look at this cluster and immediately tell me this is a young cluster because it has lots of bright blue stars, which is pretty cool that you can just do that just by looking at it. Another type of cluster we have is called a globular cluster. These tend to be incredibly dense. They have millions of stars in them sometimes, many more stars than an open cluster. But again, you can look at this picture and tell me immediately that the dominant composition of this cluster is red stars. Red stars tend to live for longer periods of time, and you don't see any blue stars to speak of. So that tells you that this cluster has to be old. Right? So we're going to do this today. We're going to use some of these observational features of clusters to figure out things like their ages, when they were formed, and also because they were all formed in the same time and place, we can use some of their properties to determine their distance. And this is going to be the next step out on the distance ladder. We're going to use the information we got from the HR diagram by using parallax to measure nearby stars to create an HR diagram, and then use that to determine the distance to distant clusters. And that's pretty powerful because as long as I can see the individual stars in the cluster to create an HR diagram in that cluster, I can tell how far away that cluster is. And if you have a powerful enough telescope, that can reach to even nearby galaxies. So this is the next step in the big distance ladder, the measurements of our distances as well. So that's what we're going to work on today. And then also today we're going to talk a little bit about the fate of low mass stars, the fate of where they wind up after they leave the main sequence and wind up in the stellar graveyard. And that's important because it turns out that most of the carbon in your body literally comes from the centers of core, or the envelopes of low mass stars. And it's kind of nice to know where the carbon in your body comes from. Okay, so first of all, let's talk a little bit more about formation, so we're very clear on where stars are coming from. We look out in the night sky and we see these star-forming clouds. What you're seeing on the left here is something called a nebula, and we can see glowing regions of the nebula and dark regions of the nebula. And the glowing regions are places where we're getting ionized gas from the stars that have already formed, and the dark regions are places where you have cool gas that's blocking the light from behind it. And inside these dense star-forming clouds, that's where we get this collapse of material that causes star formation in the first place. And the gas between this star is called the interstellar medium, and it is primarily hydrogen and helium. It has other molecules in it depending on the age of the cluster that we're talking about. And when it forms, if it can get dense enough, gravity itself will haul it together and collapse it into stars. The best place to form stars is where you can get nice, dense, cool gas, and this happens in molecular clouds. Molecular clouds, in this case, is still predominantly hydrogen, but it's now molecular hydrogen because it's cool enough that the hydrogen molecules can form together. And these things tend to be cool, as in like around the temperature of 10 degrees Kelvin. And if you remember your Kelvin scale, freezing water is 273. So this is 260 degrees below 0 centigrade. So this is incredibly cold stuff. And it's relatively dense. It has about 300 molecules per cubic centimeter. So if you imagine a cubic centimeter has 300 molecules in there, that sounds like a lot, but the air in this room probably has 10 to the 20 times as many molecules as you have in the interstellar medium. So it's dense by interstellar medium standards in these molecular clouds. But that density and that cold temperature are important, because as soon as you have a high enough density and you have a cool enough temperature, these clouds will begin to collapse on their own just simply by gravity. And once that happens, you are destined to form stars. And it's kind of neat that just a simple rule of gravity written down by Newton 400 years ago is enough to describe the basics of star formation. So yeah, I want to mention the fact that how do we know about this stuff would be a good question. As we look at emission lines from these molecular clouds, and we tend to see these mostly in radio emission with carbon monoxide, and that tells us, if we can look at the radio emission from carbon monoxide, that tells us the distribution, like this map you see in front of you, and it also tells you the relative density because we can measure the column density of the material. Okay, so this is a nice theory about where stars form. It'd be nice if we could observe them, so let's go out and look at that. What I'm looking at right here is a star field where the only thing that's interesting about it, it's just a field of stars, but the only thing that's interesting about it is this area where I don't see any stars. You just have this nice little void here where there are no stars. Now, if you just look at that, you might say, well, maybe there just aren't any stars there. But if you think about it a little bit more carefully, you would say, well, maybe there's something in the way of the star field behind it. Now, again, we don't see in 3D when we look out there. It's too far away. But it is a three-dimensional universe. And so you have stars distributed through the galaxy, and then you have stuff in between. So this is something in the visible where we see some kind of dense object that's blocking all the other material behind us. However, if I look in the infrared, I can view through that dense material because the infrared light transmits through it, even though the visible doesn't, and I can see the birth of a star. So again, if I look in the visible, all I see is a big black spot on the sky, but if I look in the infrared, I can see a little baby star just beginning to form right inside of that. So using these types of tools, we are at the point where we can observe stars in formation, which is something that is only about the last, we've only been able to do that for the last 2 decades or so. Okay, so to remind you of what we saw a couple times ago, we had that star cluster simulation video. We want to see what that results in. We start with a cloud of dust and gas. It collapses under its own gravity and forms something that we see is very, very similar to star clusters out in space. And if you look at this, these are just screen grabs from that simulation I showed you. This looks very, very similar to the pictures I showed you of open clusters, right, of young open clusters. So we think we've got a handle on what's going on here, because if we just include gravity and simple gas dynamics, we get something that looks very similar to what we see in space. Now, the two processes that are at play here when gravity starts to interact is gravity and pressure. So if you think about a gas, when I compress a gas, the pressure and temperature goes up. And once the pressure and temperature are high enough to resist the gravitational force, that gravitational collapse is going to stop. So again, we're talking at the central core of one of these star-forming cores, and it begins to collapses under its own gravitational force, and as it collapses, it heats, and the thermal pressure in the cloud begins to resist that gravitational force. Now, if we have some kind of cloud that can dissipate energy somehow, like say through emission lines, we can radiate that energy away, and the collapse will continue. So the collapse is going to continue, and the energy will be radiated away until it becomes dense enough that we no longer have emission lines. We just have a hot, dense object, and this is this thing we're eventually going to call a star. Now, if we look, I've got a little simulation here to show you of what this looks like. If I can find it here. Yeah. So let's look at a simulation here of hydrostatic equilibrium, which is this balance between pressure and gravity. Here we go. So what you're seeing here is a low mass star and a high mass star as they begin to, or as this cloud begins to collapse, right? So on the left-hand side, if we have a star collapsing and it collapses down to the radius of, say, the sun, eventually you're going to reach a point where that inward pressure from gravity is exactly balanced out by the pressure force. Now, because this is a low mass star on the left, that pressure is going to be relatively low. It's still enough to ignite hydrogen into helium in the core, but it's not enough to blow the star apart. It just comes to perfect balance. Now, in the case of a larger star, we condense, and the gravitational force is stronger, and because it's a more massive star, and therefore we have to have a higher internal pressure so that we can balance that gravitational force. But this gives the reason why high mass stars don't live as long as low mass stars, because that additional force, that additional mass pushing down on them, creates a higher pressure and temperature inside, which causes a higher rate of fusion of hydrogen to helium, which results in using up that hydrogen fuel that much faster. It also results in a much brighter star, and something you can see from a larger distance, but it also, because that extra brightness is burning through that fuel so quickly, we wind up with a star that doesn't live as long. Okay, so we now, through this form of collapse and getting to what we call hydrostatic equilibrium, where the pressure and the gravity balance each other, we wind up with what we call stars. Now, stars are objects that are balls. They are in balance, and they are so hot and dense inside that they are fusing hydrogen into helium and releasing that as energy. So that's what we call a star. One of the questions you might ask is, what types of stars are the most common and what types of stars are the most rare? Well, if we look at star clusters, and we can use those star clusters to measure the different types of stars, so we look at which ones are the low mass stars, and we look at which ones are the high mass stars, and we count up the number of stars, this is kind of the graph that you get. We get a graph that shows you that most of the stars that are formed are these low mass red stars. So if you just count it up, 200 of, if you were to have a collection of, in this case it's 261 stars, 200 of them are going to be these low mass stars. Another 50 of them are going to be stars like our sun, and then it really starts to drop off, where we get maybe 10 stars that are the next bin up, a little bit more massive than us, and only one star that's very, very, very bright. So again, we see that there's a distribution of the types of stars that are formed, and this shouldn't surprise us too much, because if we think that stars are forming by the fragmentation of a cloud, by the process of gravity, then we would expect these the fragmentation to happen more frequently at smaller scales. I mean, if you imagine just taking a teacup and smashing it against the ground, you wind up with lots of little shards and only a couple of big shards. So, if that's what's causing it, is this fragmentation of a collapsing cloud, this isn't too surprising. This does have some pretty interesting implications, though. What it means is that stars like our sun are not as common as we thought. We're not an average star. We just happen to be about even in brightness, but these low mass stars are far, far more numerous. Another reason that the low mass stars are interesting is because they tend to live a long time. So as the galaxy ages, it will collect more and more of these low mass red stars because they just haven't had a chance to fuse their hydrogen into helium and move off the main sequence of the HR diagram. Okay, so that gives us an idea of where these stars come from. Now we want to know where they're going. These stars, they form, they live on the main sequence for a time that's determined by their mass and by their brightness, and then they either slough off their material into the interstellar medium to form new stars, or they explode violently. And both of those forms are important to us because that's where everything we have on this planet comes from. Whether I'm talking about the water in my water bottle, or the plastic in my pen, or the carbon atoms in my body, they all come from the center of stars. And so this is an important process that eventually results in us. So it's something that we're pretty curious about how this happens. So now what we'd like to do is figure out how we can determine what the life cycles look like for these particular objects. So what I want to do first is talk about your activity for Thursday, because you're going to do some data analysis to examine how we can use the observations of stellar clusters to determine not only their ages, but get some sense of what the life cycle of a star looks like, and then ultimately use these clusters as a distance indicator, which is something that's very valuable for the rest of the class. Okay, so let's take a look back to our main sequence. Remind yourself that the main sequence is a plot of the luminosity on the left-hand side here. This is luminosity. And we have temperature on the bottom, right? We've got the low mass, cool stars over here, high mass, hot stars over here. And again, my rock star theory of star formation, these are the Jimi Hendrixes up here. They live fast and die young. These are the Donny Osmonds down here. They burn slow and last forever. And then the sun is right around in the middle, right about there. So this is the sun. Okay. Now the cool thing about clusters is that you're effectively taking a snapshot in time. This cluster formed at the same time, at the same distance, all of those stars in the cluster, all at pretty much the same time. So if we can take an HR diagram snapshot of that cluster, we will see the stars in that cluster and we can determine what its properties are. Now what I'm showing here is a picture of some data. These are individual stars where we have observed their luminosity and their temperature and plotted them on this HR diagram. And you can see that we have a collection of stars that form on the main sequence, but we don't see any stars up here. None. So what that tells us is that this cluster, whatever cluster we're looking at here, has to be old enough that the Jimi Hendrix stars have perished, right? They've already burned through their nuclear fuel and they're done. All right, so if we go back and look at this HR diagram, you recall that we had put some lifetimes on here based on what we knew about stellar astrophysics and how long it takes to burn through this hydrogen fuel. So I know that a star that's of a luminosity of 10 to the 5 and a surface temperature of 30,000 degrees will live for 10 million years, right? If I have a star that is 20,000 degrees and is 1,000 times the luminosity of the sun, it will live for 10 to the 8th years, right? So that's 10 times longer. The sun lives for about a billion years, or 10 billion years, so that's here down here. So if I look at data from all these different clusters, this is the an example of all the different clusters we have here. If I look at all these clusters, hang on real quick. Okay, if I look at all these clusters, I've got different clusters of different, whoops, what happened here? Different clusters here. Here's Persei, here's Pleiades, here's Hyades. These are just different clusters on the skies given by these markers. I can see that at NGC 188, I have stars that only show up on the main sequence up till here. So that means that cluster has to be somewhere between 1 and 10 billion years old. Now these stars are the evolved stars that we're going to talk about a little bit later, but I know that if there's nothing on the main sequence up here, the cluster can't be any older than that. Same thing with here, same thing with here, same thing with here, but you'll notice that these clusters get progressively younger because of where this main sequence turnoff is. Now if I want to look at that for your activity, let's go and take a look at your activity for a second. You're going to do this for several different star clusters. So what I have given you here in this Age of Stellar Clusters is a sequence of HR diagrams. Now you'll notice these are a little bit different from the HR diagrams we've been looking at because they're a graph of apparent magnitude rather than absolute magnitude. Now we're using magnitude here that's a slightly different unit than luminosity because of some historical issues with the way the Greeks used to measure magnitudes. They had it on a reverse scale, so this is, this is bright up here, even though it says 0, and this is dim down here, but same thing is true as an HR diagram. Luminosity increases as you go up. Same thing down here. This is called a color index, but again, temperature, whoosh, goes this direction, just like in an HR diagram. So if I look at any of these diagrams and I see a big long stretch like this, that looks an awful lot like my main sequence, right? The only difference is the main sequence on these charts is not showing the whole main sequence because these clusters have different ages. So your first step in this activity is to identify the tip of the HR diagram main sequence in each one of these clusters, right? And that is known as the color turnoff. And the color turnoff is effectively going to tell you the age. So if you can identify that and identify the main sequence, and I'm going to go ahead and circle the main sequence in all of these here for all these clusters. This is the main sequence for NGC 752. This is the main sequence for Hyades. This is the main sequence for M67, and this is the main sequence for the Pleiades. You'll know that that's where we have our main sequence stars that are fusing hydrogen into helium. These other stars are evolved stars that we'll get a chance to talk a little bit about when we talk about our low mass stars. So that's our main sequence there. Our goal for this activity is basically to determine three things. We want to determine which cluster is the brightest intrinsically, like which one has the brightest stars. We want to figure out which cluster is has the brightest apparent magnitude. Apparent magnitude meaning how bright it appears, because that's going to tell us which one is closer. And then we want to use the main sequence turnoff to figure out the age. right? So that's our goal for this activity. So what I thought I'd do is we just walk through the entire activity for one cluster so you can kind of see what I'm after here. So if we go up here to the top of the activity, the very first thing we want to do is identify the main sequence. So again, I'm going to choose one of these clusters and identify the main sequence. Let's take the Hyades, because we've done this one already. So I go through the Hyades, and I'm looking for any large group of stars that tracks from the upper left to the lower right. Okay, so there's my main sequence. Okay, the next thing I want to do is from where the main sequence are on these things, I want to try and figure out which cluster has the brightest stars and which one has the brightest apparently bright stars, which means they just look bright, and which ones have the brightest in absolute. So if I go down and look at these clusters again, you just have to remind yourself that the brightest stars in their apparent magnitude are going to be the ones that are highest on this graph, right? So if I just look at these two right here, I can see that the apparent magnitude for this one is lower than the apparent magnitude for this one. And again, we want to look at the brightest part of the cluster because that's what you'll be able to see. So this is the brightest part of the cluster. You can see that this one is higher than this one. So that means that this cluster has to be apparently dimmer than this one. And you can do that comparison with all of them. The other thing you might want to know is which one is intrinsically bright, and we can answer that because we know that the bluest stars are the brightest. So I look at all these things and I look for the cluster that has the bluest stars. So that means the stars that are furthest to the left in the diagram. So I don't see any blue stars over here. I don't see any blue stars over here. I go down. I'm starting to, oh, look there, we see some blue stars there. They're on the side of 0 here. I see some blue stars here, but the jewel box down here has a ton of blue stars. So we see that there are a lot of stars on the left-hand side of the diagram here. So that would be the one that is the brightest intrinsically. Now you notice it's not the highest on the diagram, but that's okay because the star could be further away or closer. That doesn't change the intrinsic brightness of the stars. So we just want the bluest stars, which are going to be the brightest ones. And once you've started to identify that, now we can look at which one is the closest or further away, because we want to look for the one that is the brightest apparent brightness compared to some reference point, right? Because we have to pick one star to do this. So what we're going to do here is we're going to give you some data that the sun has a BV color. This is its color index of 0.6. So that's just something we know from looking at the sun. The sun is a yellow-white star. So if I know that, I can go down to each one of these HR diagrams and identify where the sun would be. So I said that the sun was at 0.6. So here's 0.6 on the main sequence. So here's 0.6 right here on the main sequence. That would be right there. Here's 0.6 on the main sequence. Would be right there. Here's 0.6 on the main sequence. That's right there, right? So you see how I'm identifying the sun on that. So now I know where the sun would be if it happened to live in that cluster. Then I can measure the apparent magnitude of the sun in that cluster by just drawing a line over onto the left-hand side of the axis, right? So looking at these 4 clusters, I see that the apparent magnitude of the sun in this cluster is 14. The apparent magnitude of the sun in this cluster looks like it's 8. The apparent magnitude in this one looks like it's 14, and the apparent magnitude in this one looks like it's 10. And because we have this reverse scale, we know that we have to be higher up on the chart. Tells you how much brighter you are. We see that because this is the highest line on the chart, this cluster has to be closer than all the others because the sun in that cluster looks brighter. And that's just simply, you've got a star that you know its brightness. If it's closer, it appears brighter. If it's further away, it appears dimmer. So we can identify which one's closest just by looking at these numbers. Also, if we compare those numbers to the absolute magnitude of the sun, so this is how bright the sun really is on this scale, we have given you some more data that says that the absolute magnitude of the sun is 5. Right? So if the absolute magnitude of the sun is 5, we can tell the distance by looking at the difference between how bright the sun appears and how bright the sun is. And that's something called the distance modulus. And that's what we're going to measure here. So let's go back to our cluster. This is the Hyades. And just to do this for one of these, I know that the sun is at 0.6. So I draw 0.6 on the main sequence. I know that if I go over here, that's going to give me the apparent magnitude, which is 8, right? I also know that the absolute magnitude of the sun is 5. So if I take 8 minus 5, that's going to be equal to 3. That's my distance modulus, called the dm for distance modulus. And then once I take that distance modulus up here to the Hyades, I can say that, here's my diagram right here, that the distance modulus for the Hyades is 3. So for my distance in light years, I go up to my chart here for the distance modulus, and it's a little bit between 2.5 and 5, so that's going to be something like 200 light years. If it was exactly 2.5, it would be 100. If it was 5, it would be 300, so I just kind of split the difference. So that's going to tell us what the distance is, and we can find this distance modulus for all of the other stars. And again, this distance modulus right here is going to be the apparent magnitude of the sun minus the absolute magnitude of the sun. And the absolute magnitude of the sun is always going to be 5. The apparent magnitude is what you read off the chart. And you take the difference of those things, and you get the distance modulus. All right, and the last thing to do there is to use our turn-off color to measure the age. Because again, the older the cluster is, the redder the stars are going to be. So let's do that again for the Hyades. If I go down here to the Hyades, and I identify the turn-off color, the turn-off point of the main sequence is right there. I go down to my color and I see that that's like 0.1, right? So 0.1 on my graph of age, 0.1 is right here. I mark that and go over on this graph, and I see that that's about halfway between, what is that, 1, 2, 3, 4, 5, 6, 7, 8. That's 5 times 10 to the 8th and 1 times 10 to the 9, which means that for the Hyades with a color turn-off of 0.1, the age is halfway between 5 times 10 to the 8th and 5 times 10 to the 9, so that's like, what, 8 times 10 to the 8th years, or 800 million years. So that tells us how old that cluster is, if I counted my zeros right. 1, 2, 3, 4, 5, 6, 7, 8. Yes, that works. Okay, so that's your activity for these guys. The last thing I left you with here is just a reference HR diagram with units that you might be more familiar with. Here's our temperature scale up here that we're more familiar with. Here is our absolute magnitude scale that represents luminosity, but then you can see how BV color compares to temperature. Okay, so they're just different ways of measuring the same fact. The reason this BV color is we do it this way is because in order to measure the temperature, we have to take a spectrum and get at the peak wavelength like we talked about before, but you can also estimate the temperature just by looking at the difference between two color filters. And in this case, we used a blue filter and a visual filter with two different images to get an estimate. So we get an index which is similar to a spectrum but not as difficult to take. We can reference that to the temperature. Okay, so work on that for the next couple of days, and we will you can come back and ask me any questions you have. If you've got questions about this, you can send it over email. But just remember that those the key thing to this is identify the turnoff, identify the main sequence, and then determine the age and the distance. Now, there are a couple of other features in those clusters that we want to talk about, and that is our dead stars, right? So let's take a few minutes to talk about these, what happens to these stars as they die. Because in these clusters, you can see that there's not just the main sequence, right? There's, if I take this cluster, for example, M67, there are stars right here that are on the main sequence, and then there's all this other junk. Where did those come from? That's what we need to talk about. Now, you can already guess what the names of these things are going to be. They're bigger than the main sequence, so I'm going to call them giants, and they're redder than the main sequence, so I'm going to call them red giants, right? So that's where these guys come from. The question is, what are they, and how do we get them? So let's talk about the life cycle of a low-mass star. I'll pull up a little simulation here. So if I show you a main sequence star, this is a star that has a mass of 3.3 times the mass of the Sun. It has a luminosity of 100 times the luminosity of the Sun, and it takes it about 3.5 times 10 to the 8th years to burn through all of its fuel. Right? Now, if I happen to be less massive, then my luminosity is lower. See, the luminosity is lower. My rate of burning up the energy is lower. My mass is also lower, but it takes me longer to burn through it. If I go to very, very high mass stars, I burn through that central core helium much, much faster because I have 1,000,000 times the solar luminosity, and I only last for 10 to the 6 years. Okay, so this is the thing that controls the life cycle, how long we stay on the main sequence. But where we go after that depends on the mass of the star. Now, if I happen to have a low-mass star, and by low-mass star I mean something that's less than about 6 solar masses, then what's going to happen as this star begins to die, it's going to run out of its hydrogen fuel in the core. And when that happens, you no longer have the radiation pressure that's holding the star up. So we've had this balance between gravity and pressure. You suddenly remove the pressure, gravity is going to collapse the star. And when that happens, the core is going to collapse. Now, the core is collapsing, but the rest of this star, because the gravitation, it's now further from the core of the star, it starts to slough away because there's still some radiation pressure left over in the envelope of the star, and it starts to expand the outer envelope of the star as the core collapses. Right? And as this happens, the star gets bigger and it gets cooler from what we see. So even though the stellar core is collapsing, we see the star get bigger and cooler. And that's what makes it track up on the HR diagram. So we have a broken thermostat effectively. We have a star that is, it's not hot enough in its core to fuse anything, so the core is collapsing while at the same time we have energy that's pushing out the outer envelope of the star. Now this core is going to collapse until it reaches a point where it can fuse something, and it's going to switch fuels from hydrogen to helium. And when that happens, the core will stop collapsing, you'll produce more energy, that will cause the star to expand a little bit more, and you wind up with something called a red giant. Now the core is smaller, and you're now fusing helium into helium, helium into heavier elements instead of hydrogen into helium, but it's not going to last for very long because there's not that much helium in the core. When we fuse this helium, it turns into carbon. Right? And it requires much higher temperatures than hydrogen fusion, so it takes a while to kick in. But as soon as it does this, we start to get fusion into heavier elements. And the most important one of those is carbon, because carbon is the thing that determines largely the basis of your chemistry, and so this is where your carbon is going to come from predominantly. Now, we've collapsed this thing, and we have a core that's fusing helium into heavier elements. And when that happens, the temperature goes up very, very quickly. We get this flash of helium fusion. The helium fusion rate skyrockets and pushes out the core again, which reduces the temperature and pressure a little bit and causes it to go into the steady state for a while where it's just fusing helium into heavier elements. And this is going to last for a while, right? It's going to last for as long as it has helium fuel to burn, but it doesn't have that much helium fuel. Now, once we have this going on, we have a core where we have helium in the center, we have hydrogen on the outside, and the star is not shrinking or growing again because the thermostat has been temporarily fixed. So now we have again, for a little while, this balance between gravity and pressure. And everything's going to be fine, except in the case of a Sun-like star, this star has expanded effectively to the Earth's orbital radius and fried all life on the surface of the Earth. So as far as the Sun is concerned, everything's going on fine. Life on the Earth is over. But hey, that's going to happen. Now, once that starts to happen, you're going to run out of helium in the center eventually. You're going to have carbon in there. If you have enough mass, you can start to fuse carbon up to heavier elements, but we're going to talk about that when we talk about high mass stars. Ultimately, you're going to run out of helium fuel in the center, and when that happens, the core is going to collapse again. And in the case of a Sun-like star, it's only going to collapse to the point where it can form a basically a carbon core at the center. So I have a little simulation here of what that might look like. So this is a view from space. We imagine watching our sun die, and this is going to take, not that long, on order of a few, maybe tens of millions of years. We watch this from space. Here's our sun expanding to about the orbit of the Earth. It gets into this red giant. It goes through these kind of pulsations as it goes into its helium flash, right? Then we're going to zoom out. And what happens there is the core eventually runs out of helium to burn. It collapses into what we know as a white dwarf, and that envelope of material sloughs off into space. So let's take a look at that guy, what that looks like again. So again, we have it expand a little bit. We get our helium flash. Expands to a slightly larger level. That's about 1 astronomical unit. And then eventually the core collapses, and we get this sloughing off into space. This is not really an explosion to speak of. This is just the material gets loosely bound from this core, this white dwarf core, and returns to space. So that's where your carbon, a lot of your carbon is coming from. Now, what do these objects look like? So this is what we call a planetary nebula. Here's a picture right here. This is called a planetary nebula, not because it has anything to do with planets, but because in really crummy telescopes that they had at the turn of the last century, it looked like a fuzzy object, and they thought it was a planet, but it didn't move with respect to the stars. And you can see in here, you've got this material that has been blown off from the star by a strong stellar wind, and you see this evacuated bubble, and then right there in the middle you see a little white dwarf star. So these planetary nebulae is what our sun will eventually look like. And they have some really interesting shapes. This is a picture of one that has several bubbles on the inside. You can still see the white dwarf. There's the white dwarf right there. But you can see these kind of bubbles. And what's causing that is an area of active research. It could be because stars don't always die as pleasantly as we think they do. Maybe they go through several experiences where they're sloughing off material. But clearly it can be a complicated process, but we still see that white dwarf at the core. Here's another example of one. These are some of the most beautiful objects in the night sky. Again, you see the white dwarf in the center. You see kind of a bubble of material here, bubble of material here. And this is telling us what process happened when these stars died. Now this one is interesting because it's really it's called a bipolar because it has sort of jets coming off the sides, right? Now this looks like an eyeball in space, but if you think about taking 2 wine glasses and putting them together and then orienting like that, you've got these kind of cones coming out. And we're looking down the axis again. There's the white dwarf right there. Okay. So that's the end of our fusion. The object we get left is something called a white dwarf, and this white dwarf has enough intrinsic pressure just because of the orientation and collection of the electrons and protons in the white dwarf that it can no longer collapse under its own gravity. Now, the goal of our next discussion is going to be talking about what happens if we make that star a little bit more massive, and the result is going to be something very similar. We're going to get a very similar life cycle. The difference is the end result is not going to be a white dwarf, but it's going to be a gigantic explosion resulting in a neutron star in a black hole. But that is a discussion for next time.